Okay, welcome to lesson 1.5 part 2, where we'll discuss how do you approach an inverse function from a graphical standpoint. So what does the graph of the inverse function looks like? How could you draw the graph of an inverse function if you know the original function's graph, and so forth. So without further ado, let's dive right in. So if you want to determine the graph of a function's inverse, and you have the original function's graph already, then all you have to do is take that graph of f and reflect it across the line y equals x. And what that means is really that you're taking all your xy pairs for the graph and you're swapping them so the x's become the y's and the y's become the x's, and then that gives you the inverse function. So here's an example of a linear function f, which is actually the function 2x plus 3. And then here, the blue, we have the inverse function, which is y minus 3 divided by 2, graphed as well. And if you look at the two functions' graphs on the same axes, and when you're graphing these two functions together, you really do actually need to plug in x minus 3 over 2 to graph them together on Desmos or on your graphing calculator. You should see that they're symmetric, and the line of symmetry is the line y equals x. So here's y equals x, which is our line of symmetry running through in between these two functions. So there's y equals x. And so if you've got the graph of f, then all you need to do is take all the points on that graph and swap their x and y values, and that gives you the graph of the inverse. Okay? So let's look at a couple of examples of points that we could take. So this point right here, which is 0, 3. If we swap the x and y values for 0, 3, that gives us the point on the blue graph, which is 3, 0. So this point that's 0, 3, we can see that it reflected across the line y equals x and became the point 3, 0. And we can do this for other points as well. We could look at this point, say, this point up here, which is 2, 7, and we can find its pair, its buddy on the blue graph, the inverse, which is 7, 2. 7, 2 is going to be the point reflected across the line y equals x. So 2, 7 on the original function is now 7, 2 on the inverse function's graph. Okay? Let's look at some more things about inverses graphically. So why does this work? So if that point, say 2, 4, is on the graph of f, what that means at its heart, what that really means is that if you plug 2 in to your function, then you get 4 out as the answer. Okay? So what this means is that 2, the input 2, gives you the output 4. Okay? So since the inverse is the machine backwards, you're plugging y's in, getting the x's out. Then if you plug 4 into the inverse machine, that's going to give you 2 as the answer. And so you can see this 4 was the output, and it's giving us 2, which was the input, as the answer. And so then that tells you that 4, 2 is on the inverse function's graph. So we can see that 2, 4, which is the original point on f, says f of 2 equals 4. The inverse function says f inverse of 4 equals 2, and so that gives us 4, 2 on the graph of the inverse function, which is switching the x's and y's. Okay, so here's an example. We've got, this is the x squared graph. So we have x squared, with the domain x greater than or equal to 0. That's starting at 0 and going up. Remember, parabolas, we're not allowed the entire domain to make them one-to-one. We have to take a subset of the domain. So our domain in this case is 0 to infinity in order for it to be one-to-one. And the blue graph over here is its inverse function, which is the square root function, root x. Okay, it's the undoing function for x squared. And so you can see some points get flip-flopped, right? Our point here, which is 2, 4, ends up going to 4, 2 over here. So that's where it ends up. And again, the reason for this is that f of 2 is 2 squared, which equals 4. And so the inverse function says f inverse of 4 is root 4, which is 2. It's the inverse, right? It's the undoing function. So when we plug 4 into the inverse, we get 2 as the answer. When we plug 2 into the original function, we get 4 as the answer. And you can see they also share this point, 1, 1, right? 1, 1 is on both the inverse and the original function. And why is that on both graphs? There's a lot of reasons, right? For one, when you plug 1 into x squared, you get 1 out. So if you plug 1 into the inverse function, you get 1 as the original input. And 1, 1 is on the line of symmetry for those two functions, right? The line of symmetry is y equals x. 1, 1 has the same x and y. So when you swap them, nothing happens. It stays where it is. Okay? And that happens for any point that's on that line of symmetry. So any point on the line of symmetry is not going to move, which is the line, again, y equals x is our line of symmetry for inverse functions. Y equals x. That's hard to read. Let's do y equals x over here. Y equals x. That's the line of symmetry for inverse functions. So if you find a point that has the same x and y value, then it's on both the original functions graph and the inverse functions graph. Okay? All right. So one thing to note is that if you've got a horizontal asymptote, so you've got a one-to-one function, and it has a horizontal asymptote at some value, for example, c, then the inverse function will have a vertical asymptote at that same value, and vice versa. So here's an example of a function with a horizontal asymptote and a vertical asymptote with both. You can see the vertical asymptote is right here when x equals 1. So we've got a vertical asymptote here for x equal to 1. So that means 1 is not an allowed value to plug in. This is actually the graph of, in case you're curious, 1 over x minus 1. It's the 1 over x graph moved to the right one. And it has a horizontal asymptote as well right here when y equals to 0. So it never hits 0. So from this graph, we can read the domain and range, right? The domain is going to be everything except for 1. So I'll just succinctly say x cannot be 1. And the range, we can see from the graph, is everything except for 0. So we'll just say succinctly y cannot be 0. So when we look at the inverse function, we know those domains and ranges flip. They flip from each other. And you'll get something that looks like this. It has a vertical asymptote when x equals 0. That was the horizontal asymptote of the first function, the original function. It has a horizontal asymptote when y equals 1, at y equals 1, which was the vertical asymptote of the original function. And you can imagine what's happening here is we took a horizontal line, and when we reflected across the line y equals x, it actually turned into a vertical line. And when we had a vertical line, when we reflected across the line y equals x, it turned into a horizontal line. And so that's what's happening to these asymptotes, is that they are getting reflected as well as all the points are getting reflected. So, you know, we can kind of see where some of these points went, like 2, 1 right here. That went to, whoops, that went to 1, 2, and so forth. You exchange the x's for y's and the y's for x's. So what was originally a horizontal asymptote of y equals became an x equals. And what was a vertical asymptote in x equals became a y equals. Okay? All right. So those asymptotes are going to flip as well as all the points. All right? Okay. Yeah, just to note, domain and range for this one. So the domain is going to be x cannot equal 0, and the range is going to be y cannot equal 1. All right. Okay, something along with the horizontal line test that will help us determine whether you can, whether a function's one-to-one, is a notion of increasing and decreasing. Now, I didn't talk about this yesterday because this is kind of, or the last lesson, because this is kind of in the graphical approach to thinking about inverses. The horizontal line test could have been there too, but I thought that was pretty intuitive. So increasing means that the function gets bigger as you move to the right. So as you go to the right, your function's values are increasing. And decreasing means the function's values get smaller as you go to the right instead. So they go down and to right and down. And here are some the mathy definitions for increasing and decreasing. And we'll kind of like plot it in general, and then we'll look at a particular case of what this looks like. So we'd say a function is increasing on an interval, an interval that contains these values, or these inputs a and b. If the value at a is smaller than the value at b, when a is smaller than b. So what does that look like graphically? Well, it looks something like this. You've got your functions graph, and let's say a is smaller than b, so that means a is left of b. You know, it could be 1 and 5, right? Or it could be -2 and 0. But as long as a is smaller than b, this would be what, you know, the interval we're interested in. And then the value, maybe f of a is something like 1, so its value would be right here. So we would plot a f of a. And you want the value to be smaller than the value at b. So f of b is going to be above f of a. And so your function would, you know, get bigger as you go. And it holds for all the a's and b's that are in that interval as long as a is smaller than b. Okay. So it's kind of our shape. For a function to be decreasing on an interval, then it's like the opposite is true for those values. Now, instead of each b value being more than the value at a, it's now less than the value at a. So as you go to the right, you instead go, you instead go down. So you're going right and down on the graph. And so what that would look like is kind of the reverse of this. So I'm just going to go ahead and erase this and erase that. And now we're going to look at what happens. Let's just use a different color. So for decreasing, this is the picture you should have. A is still smaller than b, meaning we're still looking at values to the right. And now f of a is the bigger one. So here's f of a is up here, and f of b is down here. And so our function has to go from this top point to this lower point somehow, so it could curve or it could go straight, but the values get smaller as you move to the right. So you go smaller as you move to the right, and that's decreasing. And then you would say it's increasing in general if that holds over the whole domain, if the values get bigger as you move to the right, and it's decreasing in general if you get smaller as you go to the right. Okay? So those are our two notions of increasing and decreasing. And how this helps us is that if it's increasing on this interval, it's 1-to-1 on that interval. And if it's decreasing on an interval, then it's also 1-to-1 on that interval. And that really increasing and decreasing should really stick in your head that really has to do with the 1-to-oneness part, because if it's getting smaller, it's dipping down, it has to, there's no common y value. Unless it starts to dip back up, and then it's no longer decreasing on that interval, because then it's going back up, and it would be increasing. Okay, so here's an example of a function that is increasing over the whole domain. And the function 2 to the x is what we've got graphed here. So when you plug in 0, you get 1. When you plug in 1, you get 2. When you plug in 2, you get 4, and so forth. When you plug in -1, it gives you a half. And this function is increasing because as you go to the right, you go up, and you go up, and you go up, and you go up as you go to the right. And every f of b is more than every f of a, as long as b is more than a. So whenever we're to the right, for example, 1, and we could use -1 and 1 as a and b, and we can see the value here is 1/2, and the value here is 2, and so that increasing property holds. F of 1 is more than f of -1. That holds no matter what your two values are, as long as the b value is to the right is more than the a value. That's increasing. And here's an example of a decreasing function. This function is 1/x. Now it's decreasing on two different intervals. It is not decreasing in general, because if I were to look at 1 and -1, then it's not decreasing because the values are -1 and 1, and to get from here to here, right, you can see it kind of like it's higher on the right than it is on the left, and so it's not decreasing in this case. But oops, let's get my eraser. But if you just look at chunks of it, if you just look at this chunk, say the left chunk, then you can see as you go right, you go down, 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 you go down as you go right. So everything from -infinity to 0 is a decreasing function. So it's decreasing on that interval from -infinity to 0. And the same is true if you were to look at the other interval from 0 to infinity. Starting up here, you go right and down, 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 right and down. So it's going right and down for all these values on the interval from 0 to infinity. And so it's decreasing here, it's decreasing there. But in general, you could say this function would not be decreasing because you've got, you know, if you look at this point and this point, it does have to increase like that. Okay? All right. So this is a example of increasing and decreasing, and you can see when these functions are increasing and or decreasing, then they're 1-to-1, right? They're 1-to-1 functions. Okay, another thing we can do with inverses is we can look at a inverse from a table. So a function is 1-to-1 if there's no repeated values in the f of x column. So that's the column of y values. It's not 1-to-1 if there are repeated x values. And then if there are no repeated x values in the y or f of x column, then you can get the inverse function just by swapping columns. That's all it is. You're interchanging the x and y values. So suppose we have this function, f of 2 is -1, f of 3 is 0, f of 8 is -4, f of 10 is √2. So these are our inputs are over here on the right, or on the left. These are the inputs. And then these are the outputs over here. We'd plug 2 in, get -1 out. Then the inverse function is simply as we can see, it's 1 to 1, right? There's no common outputs over here. There's no two x's that go to the same y value, because -1, 0, -4, √2 are all different numbers. Then it's 1 to 1, and we get the inverse function like that. The inputs of the inverse function are values from the output column of the original function. And then the outputs of the inverse function are the original x's you would plug in to get those outputs. So if you plug -1 into the inverse function, it gives you 2 as the answer. If you plug 0 into the inverse function, it gives you 3 as the answer, and so forth. So it's basically running this machine backwards. So it's sending you back from where you came from, whereas the original function was sending you forwards from 2 to -1, 8 to -4, 10 to √2, and 3 to 0, and so forth. Okay, so that's simply inverses from a table. All right, so let's look at an example. So first, let's look at this function 2 to the x. Is this function 1 to 1? And the answer to that is yes, it is 1 to 1 because it's increasing for all x's, right? It's increasing over the whole domain. And we can see the function is increasing. If we were to sketch its graph, then you would see that as you go right, you go up. So it is going to be an increasing and 1 to 1 function. There are no, passes the horizontal line test totally. Okay, now let's sketch the graph of the inverse function. So to sketch the graph of the inverse, remember we just take each point and we reflect it across the line y equals x. So 0, 1 is now 1, 0, 1, 0. And 1, 2 is now 2, 1, 2, 1. 2, 4 is now 4, 2. Okay, getting a hang for it. This point over here, -1, where is it? -1 and 1/2 becomes 1/2 -1. So we plot that right here. This point over here, -2 and 1/4 is now 1/4 -2. And you can see that we're going to get closer and closer to the the y-axis, but we're actually never going to hit it. And so we end up having a vertical asymptote when y equals 0. So this would be what our function looks like. And there's a vertical asymptote, x equals 0. X equals 0. And remember, this should match up with what we said earlier. Our horizontal asymptotes become vertical asymptotes for the inverse function. Okay, so, boom, there it is. That's the inverse function. Let's go ahead and erase all my, no, you can see it under there. Yeah. So there's their inverse function. We can discuss the domain and ranges of these two functions. The domain from 2 to the x is all real numbers, and its range from 2 to the x is everything strictly more than infinity, or more than 0. Everything from 0 to infinity. And from the inverse functions graph, we know that these domains and ranges swap, so the inverse function domain is from 0 to infinity, not including, which is why there's that vertical asymptote at 0, and then the range is going to be all real numbers, because the domain of the original was all real numbers. Okay, let's look at a table of values as well for f and f inverse. So for the function f, we can plug -2 in, -1, 0, 1, and 2. Remember, this is 2 to the x, so let's do a couple of these together. 2 to the -2 is equal to 1 over 2 squared, which is 1 over 4. So this should be 1/4. And 2 to the -1 is 2 to the -1, which is 1 over 2. And 1 over 2 to the 1 is 1/2. 2 to the 0, any number to the 0 power, you should have learned, is equal to 1. 2 to the 1, that's equal to 1. 2. 2 to the 2, that's equal to 4. And so that's our table of values for the original function. And the table of values for the inverse function is just a swap of x and y values. So the inverse functions table looks like this. Plug in a quarter, and that gets you -2. Plug in a half, that gets you -1. Plug in 1, that gets you 0. Plug in 2, that gets you 1. Plug in 4, that gets you 2, right? It's the outputs of the original function become the inputs of the inverse, and the inputs of the original function become the outputs of the inverse. And that's the whole shebang. Inverses from tables and graphically, and this approach of reflecting across the line y = x, that line of symmetry. And we'll get some practice with this tomorrow prior to your unit test that's on Friday. So hopefully you learned something in this video, and I'll see you guys in class tomorrow.